Hello, and welcome to Space for Sleep. The James Webb Space Telescope is not a telescope that looks at the beginning of time in a magical sense. It does something more precise, and in some ways more astonishing. It catches light that has been traveling since the universe was very young. Every telescope is a time machine. The moon is seen as it was a little more than a second ago. The sun is seen as it was about 8 minutes ago. The nearest stars are seen as they were years ago. A galaxy billions of light years away is seen as it was billions of years in the past. But Webb was built to push this ordinary truth to an extraordinary limit, to see galaxies whose light began its journey when the universe was only a few 100 million years old. That goal shaped everything about the telescope. It had to be large, because the earliest galaxies are faint. It had to see in infrared light, because cosmic expansion stretches ancient ultraviolet and visible light into longer wavelengths before it reaches us. It had to be cold, because a warm infrared telescope would glow in the very wavelengths it was trying to measure. It had to unfold in space, because no rocket fairing could hold a 6.5-meter mirror and a tennis court-sized sunshield in their working shape. It had to go far from Earth, to a stable region near L2, where the Sun, Earth, and Moon could remain on one side of the observatory and the cold telescope could look outward into deep space. On Christmas Day 2021, an Ariane 5 rocket lifted off from the Guiana Space Center, carrying the most complex astronomical observatory ever sent into space. Webb had taken decades to design and build. It had cost billions of dollars. It had survived delays, redesigns, testing failures, political pressure, budget criticism, and the constant knowledge that once it launched, no astronaut repair mission was planned. Then came the unfolding. The telescope had been packed for launch like an engineered origami sculpture. Its mirror wings were folded. Its sunshield was folded. Its secondary mirror had to extend. The 5-layer shield had to separate, tension, and hold its shape. Hundreds of mechanisms had to work in sequence. The mission team had rehearsed everything on Earth, but Earth could not reproduce the exact conditions of space. Once the telescope was released, there was no way to walk up to it and adjust a stuck hinge. And everything worked. That sentence is easy to read quickly, but it is one of the great engineering facts of modern astronomy. Everything worked. The sunshield deployed. The mirrors unfolded. The telescope cooled. The mirror segments aligned. The instruments came alive. Webb reached its orbit near L2 and began doing the job it had been built to do. On July 12, 2022, NASA, ESA, CSA, and the Space Telescope Science Institute released Webb's first full-color science images and spectra. The first deep field showed thousands of galaxies in a patch of sky about the size of a grain of sand held at arm's length. The spectrum of WASP-96b showed water vapor and evidence for clouds and haze in the atmosphere of a distant hot gas giant. The Carina Nebula revealed previously hidden star birth inside dust. Stephan's quintet showed galactic interaction in infrared detail. The Southern Ring Nebula exposed layers of dust and gas around a dying star. Those first images were not the end of a project. They were the opening of a new observational era. Since then, Webb has found and confirmed galaxies so distant that their light comes from only a few 100 million years after the Big Bang. It has identified JADESGS Z14-0 at a redshift of about 14.3, and then pushed even closer to cosmic dawn with MOM Z14, confirmed at a redshift of about 14.4 and seen when the universe was about 280 million years old. It has measured exoplanet atmospheres in unprecedented detail, including the first clear carbon dioxide detection in an exoplanet atmosphere at WASP-39b. It has studied TRAPPIST-1 planets and found no definitive signs of atmospheres yet. It has looked into star-forming clouds, mapped dust and molecules, studied solar system worlds, detected carbon dioxide on Europa's surface likely connected to its subsurface ocean, and revisited famous objects like the Ring Nebula, Cassiopeia, and the Pillars of Creation with a new infrared eye. This is why Webb is such a strong subject. It is not only a machine for beautiful pictures, it is a machine for turning invisible light into history. It shows us galaxies before the Milky Way existed in its present form, planets whose air we can never touch, stars still hidden in their birth clouds, and dust left behind by dying suns. The story of Webb is the story of a telescope built to make the invisible universe measurable. The story of the James Webb Space Telescope begins with the story of the Hubble Space Telescope, because Webb was conceived as Hubble's successor, and its capabilities make sense only in relation to what Hubble achieved and what Hubble could not do. Hubble launched in April 1990 and was immediately discovered to have a flaw in its primary mirror, a manufacturing error of 1.3 micrometers in the mirror's shape, less than a 50th the width of a human hair, that nonetheless produced severely blurred images. The error was caused by a precisely wrong calibration in the device used to check the mirror's shape during grinding, and it resulted in every image Hubble took being noticeably blurred by spherical aberration. The flaw was embarrassing to NASA, damaging to the agency's public credibility, and a scientific catastrophe for the community that had waited decades for Hubble's capabilities. The solution, a corrective optics package installed by Space Shuttle astronauts during a servicing mission in December 1993, was one of the most dramatic engineering rescues in the history of space exploration. The astronauts performed 5 spacewalks over 11 days, replacing instruments with corrected versions and installing a device called COSTAR, Corrective Optics Space Telescope Axial Replacement, that effectively compensated for the mirror's error by introducing an equal and opposite optical error in the light path before it reached the scientific instruments. The fix worked. Hubble's images, after servicing, were as sharp as they were supposed to be from the beginning. What followed was 3 decades of extraordinary scientific productivity. Hubble determined the Hubble constant with unprecedented precision, advancing the age measurement of the universe. It showed that the universe's expansion is accelerating, contributing to the discovery of dark energy. Its deep fields, long exposures of apparently blank patches of sky that revealed thousands of distant galaxies, showed that the universe is filled with structure to the furthest distances observable at optical wavelengths. It characterized the atmospheres of planets in our solar system, measured the masses of black holes through the kinematics of stars near galactic centers, monitored the surfaces of planets in extraordinary detail, and provided spectacular images of nebulae, star clusters, and galaxies that became the public face of astronomy for an entire generation. But Hubble had a fundamental limitation that no servicing mission could overcome. Its mirror was too small, and it operated primarily at visible and ultraviolet wavelengths rather than in the infrared. The size limitation matters because light gathering power scales with the area of the primary mirror, which scales with the square of the diameter. Hubble's mirror is 2.4 meters across. Webb's is 6.5 meters, more than 2.5 times the diameter, meaning more than 6.5 times the light gathering area. For faint, distant objects, this difference is enormous. The wavelength limitation matters even more for the specific goal of studying the earliest universe. The universe is expanding, and the expansion stretches the wavelengths of light traveling through it. Light emitted in the ultraviolet by galaxies in the young universe, traveling for 13 billion years through expanding space, arrives at Earth shifted to much longer wavelengths, into the infrared, which the human eye cannot see and which Hubble's instruments were not primarily designed to detect. The most distant galaxies, the ones closest in time to the Big Bang, are essentially invisible to Hubble at visible wavelengths. their light arriving entirely in the infrared. Detecting and studying those galaxies required a much larger telescope operating at infrared wavelengths. These requirements shaped the design of Webb from the beginning. The goal of seeing the first galaxies that formed after the Big Bang, perhaps a few 100 million years into the universe's history, determined that the telescope needed to detect light redshifted from ultraviolet and visible wavelengths into the near and mid-infrared, roughly 0.6 to 28 micrometers. The telescope's mirror had to be large enough to detect these extremely faint signals. And the telescope itself had to be extraordinarily cold, because infrared detectors are sensitive to any thermal emission from the telescope's own structure, and a warm telescope would be blinded by its own glow. This requirement for cold created the design's central engineering challenge. Hubble operates at Earth's distance from the Sun, where maintaining a low temperature is difficult, and it keeps its mirror and instruments at ambient space temperature, not very cold. Infrared astronomy is the key to understanding Webb, and it is worth slowing down for it. Human eyes see only a small part of the electromagnetic spectrum. Hubble became famous largely through visible light and ultraviolet views of the universe, wavelengths close to the light our eyes evolved to use. Webb works mostly beyond that familiar window. It sees wavelengths longer than red light, wavelengths associated with heat, dust, molecules, old starlight, and ancient light stretched by cosmic expansion. This makes Webb powerful in 3 different ways. First, infrared light can pass through dust more effectively than visible light. A star-forming region that looks dark or opaque to Hubble may reveal embedded protostars to Webb. Dust does not vanish in infrared, but it becomes less blinding. This is why Webb can see young stars inside clouds and warm dust inside planetary nebulae. Second, many molecules leave strong fingerprints in infrared light. Water vapor, carbon dioxide, methane, carbon monoxide, silicates, organic molecules, and many other species absorb or emit at infrared wavelengths. This makes Webb a chemistry machine. It does not merely photograph planets, disks, or nebulae. It can measure what they are made of. Third, the most distant galaxies have had their light stretched into the infrared by the expansion of the universe. A young galaxy may have emitted ultraviolet light from hot newborn stars, but by the time that light reaches Webb, it has been redshifted far beyond visible wavelengths. To see cosmic dawn, astronomers needed an infrared telescope. The same design, therefore, serves several sciences at once: star birth, planet formation, exoplanet atmospheres, dusty galaxies, black holes, dying stars, and the early universe. Webb is not only bigger than Hubble, it is tuned to a different hidden layer of reality. Webb needed its mirror and instruments to operate at approximately -233 degrees Celsius, just 40 degrees above absolute zero, to avoid thermal self-emission at the wavelengths of interest. Achieving this required either active cooling with cryogenic refrigerators or passive radiative cooling by placing the telescope in a location perpetually shaded from the sun and allowing the mirror to radiate its warmth to the cold of space. The solution was both passive cooling shielded by the enormous sunshield, with the near-infrared instruments operating passively at about -233 Celsius, and an additional active cryocooler for the mid-infrared instrument, MIRI, which needs to operate at -266 Celsius, just 7 degrees above absolute zero. The sunshield achieves the temperature separation by blocking sunlight and earthshine from ever reaching the cold side of the telescope. Webb orbits not around Earth, but at the second Lagrange point, L2, a point in space roughly 1.5 million kilometers from Earth in the direction opposite the Sun, where the gravitational pull of the Sun and Earth together causes an object to maintain its position relative to the Earth-Sun line. At L2, Webb keeps the Sun, Earth, and Moon all on the same side, allowing the sunshield, always oriented toward the sun, to shade the entire telescope, mirror, and instruments in permanent shadow. The hot side of the sunshield, facing the sun, reaches temperatures of roughly 90 degrees Celsius, warm enough to boil water. 5 layers of insulating film later, the cold side sits at minus 235 degrees. L2 is not a parking spot in the ordinary sense. Webb does not sit motionless at L2. It follows a large halo orbit around the L2 region, maintaining its position with occasional station-keeping burns. The reason this works is that L2 lets Webb keep the Sun, Earth, and Moon all in roughly the same direction. That geometry is what makes the sunshield possible. The telescope can keep its hot side facing the Sun and its cold side facing deep space. This geometry also gives Webb a wide view of the sky over the year, though it cannot point just anywhere at any time. The sunshield must remain properly oriented, so each target becomes observable during certain windows. Webb's schedule is therefore an intricate puzzle of science priority, sky visibility, instrument configuration, thermal stability, data downlink, and calibration. A telescope like Webb is not simply looking wherever someone wants it to look. It is living inside a carefully managed geometry. The primary mirror is the heart of the telescope and the feature that required the most novel engineering. 6.5 meters of primary mirror diameter is far too large to fit inside any available rocket fairing in a conventional rigid form. Webb's mirror had to be built to fold. The solution is 18 hexagonal segments of beryllium, a lightweight, structurally rigid metal with excellent cryogenic properties, each coated with a thin layer of gold, which reflects infrared light more efficiently than any other common coating material. The segments are arranged in a honeycomb pattern, 12 outer segments forming the rim of the mirror, 6 inner segments, and a central blank where the secondary mirror structure blocks the view. When unfolded, they form the familiar gold hexagonal array that has become Webb's most recognizable visual feature. Each segment is mounted on actuators, 6 fine movement actuators per segment, plus one that adjusts the segment's curvature, allowing each to be precisely positioned to within nanometers of its target location. The initial deployment, releasing the segments from their launch locks, brings them to roughly the right positions. Then a weeks-long process of wavefront sensing and control, using the light from a single star to measure how far each segment's reflected image deviates from perfect focus, gradually adjusts each actuator through iterative sequences until the 18 segments are co-phased, aligned so precisely that they act as a single, continuous mirror surface rather than 18 separate pieces, with segments aligned to within about 150 nanometers of their target positions. This alignment process was one of the most anxiously anticipated engineering milestones of the early commissioning phase. It had been rehearsed extensively on the ground, but the actual performance of the actuators in the thermal environment of L2, cold, stable, and without the Earth's gravitational pull distorting results, could only be confirmed after launch. The wavefront sensing images, released by NASA in February 2022, showed 18 separate images of the same star gradually converging into a single, sharp point as the segments were brought into alignment. The moment of alignment produced a single image of unprecedented sharpness that demonstrated the mirror was performing to its specification. The 4 scientific instruments aboard Webb cover different wavelength ranges and provide different observational capabilities, collectively allowing the telescope to address an enormous range of scientific questions. The near-infrared camera, NIR-CAM, is the primary imaging instrument and the telescope's main wavefront sensing tool during commissioning. It operates from roughly 1 to 5 micrometers in wavelength and provides the deep, wide-field infrared images that have become Webb's most recognizable public output. The images of galaxy clusters and distant galaxies, that NASA has released as demonstration of the telescope's capabilities. The Near-Infrared Spectrograph, NIR-SPEC, can simultaneously observe up to 200 individual galaxies in a single pointing. Using a microshutter array, a grid of hundreds of thousands of individually programmable tiny shutters, each about 100 micrometers wide, that can be opened or closed to select specific objects within the field of view for spectroscopic observation. This capability for massively multiplex spectroscopy, observing hundreds of objects at once, is one of the features that makes Webb particularly powerful for statistical studies of galaxy populations at cosmic distances. The Near-Infrared Imager and Slitless Spectrograph, NIRISS, provides additional imaging and spectroscopic capabilities in the near-infrared, and is particularly valuable for studying the atmospheres of transiting exoplanets through transmission spectroscopy. The Mid-Infrared Instrument, MIRI, extends Webb's wavelength coverage from 5 to 28 micrometers, the mid-infrared range. At these wavelengths, Webb can detect the thermal emission of objects at temperatures of a few hundred Kelvin, see through dusty molecular clouds to observe embedded protostars, characterize the chemistry of protoplanetary disks, and study the most distant, most strongly redshifted galaxies whose light has been shifted entirely into the mid-infrared. MIRI's active cryocooler, which cools it to -266 Celsius, was one of the most technically challenging components of the whole observatory. Together, the four instruments give Webb an observational versatility that no previous telescope has matched, the ability to study objects from the nearest planets and moons to the most distant galaxies ever observed, in wavelengths spanning the full near to mid-infrared range, with imaging, spectroscopy, and coronagraphic capabilities all available. The commissioning phase is one of the most satisfying parts of Webb's story because it turned anxiety into precision. After launch, Webb did not instantly become a telescope. It was a spacecraft first, then a folded structure unfolding, then a cold observatory cooling, then 18 separate mirror segments acting like 18 separate mirrors. The alignment team had to identify which blurred star image came from which segment. They had to move each segment through tiny actuator steps, stack the images, focus them, and then co-phase the mirror so the segments behaved as one optical surface. The first alignment images were not glamorous in the public image sense. They were engineering images, dots, patterns, repeated star images, diagnostic plots. But those images were the proof that the telescope could become itself. This is another reason Webb feels different from a normal launch success. A rocket launch either reaches orbit or does not. Webb had to succeed gradually. It had to keep becoming more precise over weeks and months, as each subsystem crossed from possibility into reality. When the first fully focused star image appeared, surrounded by background galaxies that had slipped into the frame almost casually, it showed two things at once. The mirror worked, and the universe behind the test star was already waiting. The first science images released by NASA and its partners in July 2022 were chosen to demonstrate the telescope's capabilities across its full range of science objectives, and they were received worldwide as a demonstration that Webb was meeting or exceeding its design goals. The Deep Field image, Webb's Deep Field, showing a tiny patch of sky about the size of a grain of sand held at arm's length, contained thousands of galaxies at a range of distances, with the most distant among the faintest and reddest, their light having traveled for more than 13 billion years to reach Webb's mirror. The image was assembled from observations at several wavelengths and combined into a single color composite, with infrared wavelengths mapped to visible colors in a scientifically informative scheme. The sharpness and depth of the image was immediately comparable to the iconic Hubble deep fields, and in some respects exceeded them at the infrared wavelengths where Hubble's sensitivity is limited. The spectrum of WASP-96b, a hot, puffy gas giant about 1,100 light-years from Earth, showed a detailed transmission spectrum revealing the presence of water vapor and evidence for clouds and haze in the planet's atmosphere. The spectrum was obtained by measuring the dimming of the host star's light as the planet transited, and comparing observations taken in transit with those taken outside transit to isolate the wavelength-dependent absorption signature of the atmosphere. The richness and clarity of the spectrum demonstrated Webb's capability for exoplanet atmospheric characterization in a single, relatively short observation. The Carina Nebula image showed the cosmic cliffs, a towering wall of molecular cloud material, in the star-forming region NGC 3324, in near-infrared light that penetrated the dust to reveal dozens of previously unknown protostars embedded in the cloud, visible as bright red points of light, with jets of material shooting from their poles. The image was simultaneously spectacular as a visual object and scientifically rich, showing the detail of star formation processes in a nearby region with unprecedented clarity. Stephan's Quintet, a visual grouping of 4 physically associated galaxies and 1 foreground galaxy, was shown in a wide-field composite image covering a region of sky larger than the other first-release images, demonstrating Webb's ability to map extended regions as well as deep, narrow fields. The image showed the complex web of star formation, gas stripping, and gravitational interaction between the 4 associated galaxies in the group, with structures visible in the infrared that had not been seen in previous optical images. The Southern Ring Nebula, a planetary nebula about 2,500 light-years away, was shown in both near-infrared and mid-infrared images that revealed different aspects of the ejected stellar material structure. The mid-infrared image in particular showed concentric shells of dust and gas extending far beyond the main visible nebula, multiple ejection episodes preserved in the expanding shell structure, and characteristics of the central binary star system that could not be inferred from optical observations alone. The detailed morphology of the Southern Ring Nebula that Webb revealed in a single observation will inform models of planetary nebula formation and of the binary stellar interactions that drive much of their structural complexity. These first images established immediately that Webb was not merely a marginal improvement over previous observatories, but a genuinely transformative capability, a telescope that would not simply add incremental data to existing knowledge, but open entirely new domains of observation. The first images also taught an important public lesson. Webb's colors are translated. The telescope records infrared light. Human eyes cannot see infrared. To make Webb images visible, different infrared filters are mapped into colors we can see. Shorter infrared wavelengths may be assigned blue, longer infrared wavelengths red, and intermediate wavelengths green or orange. The result is not fake. It is data translated into human vision. This matters because the images look artistic, and people sometimes mistake beauty for invention. But the structures are real. The colors encode differences in wavelength, temperature, dust, emission, and composition. In a nebula, red may reveal warm dust or molecular emission. In a galaxy field, red may indicate extreme distance or dust. In an exoplanet spectrum, a bump at one wavelength may mean water or carbon dioxide absorption. Webb's beauty is not separate from measurement. It is measurement made visible. That is why the first images worked so well. They gave the public a door into the science without removing the science behind the door. Among Webb's most productive scientific programs in its first years of operation has been the study of exoplanet atmospheres, particularly the atmospheres of rocky planets in the habitable zones of their host stars. As discussed in the exoplanets episode, the TRAPPIST-1 system, 7 Earth-sized planets around a small, cool red dwarf star 40 light-years from Earth, with 3 planets in or near the habitable zone, is the priority target for rocky planet atmospheric characterization with Webb. The system's nearby distance and favorable geometry make it the best available opportunity to search for atmospheric signatures on potentially habitable rocky worlds. Webb's observations of TRAPPIST-1b in 2023 used the secondary eclipse technique, measuring the total thermal emission of the planet when it disappears behind the star and comparing it to the total emission when both planet and star are visible, allowing the planet's own emission to be isolated. The planet's dayside temperature, inferred from this measurement, was higher than expected for a world with no atmosphere, consistent with a bare, airless rock absorbing solar energy and re-emitting it as heat without any atmospheric redistribution. This result strongly suggested that TRAPPIST-1b lacks a substantial atmosphere. The observation of TRAPPIST-1c produced a similar result. The planet's thermal emission was consistent with a bare rocky surface rather than a planet with a significant carbon dioxide atmosphere, which models had suggested as one possible atmospheric scenario. TRAPPIST-1c is slightly farther from the host star than TRAPPIST-1b and receives less radiation, making its atmospheric loss somewhat less certain. The result doesn't definitively rule out a thin atmosphere, but it constrains the atmospheric scenarios significantly. By late 2025 and into 2026, the larger picture of TRAPPIST-1 had become more cautious. Webb data had been collected for all 7 planets, but the community had reported detailed results for B, C, D, and E. So far, Webb had found no definitive signs of an atmosphere around any of the observed worlds. The inner planets B and C showed little evidence for thick atmospheres, with B looking increasingly like a bare rock and C, if it has air at all, likely having only a thin atmosphere. For D and E, the data remained under study, but thick hydrogen-rich atmospheres had been ruled out. That does not mean the habitable zone planets are airless. It means the question is harder than early public expectations suggested, and stellar activity from the red dwarf complicates the interpretation of every transit. Beyond the TRAPPIST-1 system, Webb has characterized the atmospheres of several larger, warmer planets in detail unprecedented by previous telescopes. The detection of sulfur dioxide in the atmosphere of WASP-39b, a hot Saturn mass planet, through a photochemical process driven by stellar ultraviolet light, was particularly significant, demonstrating that Webb could detect not just the primary atmospheric constituents, but the products of atmospheric chemistry driven by stellar radiation. This capability will be essential for detecting biosignature gases in future observations of potentially habitable planets, where the specific chemical signatures of biological activity may be subtle and embedded in the context of complex photochemical processes. The detection of carbon dioxide in the atmosphere of WASP-39b was the first clear detection of CO2 in an exoplanet atmosphere, achieved in a single observation that demonstrated the sensitivity improvement Webb provides over previous capabilities. This is where Webb changed expectations and, at the same time, made the story more sober. Before launch, many people hoped Webb would quickly find atmospheres around small rocky planets. That hope was understandable, but the observations are difficult at the edge of what even Webb can do. A rocky planet blocks only a tiny fraction of its star's light. Its atmosphere, if it has one, changes that blocked light by an even tinier amount. Around active red dwarfs, star spots and flares can imitate or contaminate planetary atmospheric signals. The telescope is powerful, but the measurement is unforgiving. This is why non-detections matter. A result showing that TRAPPIST-1b is likely airless is not a failure. It is a real constraint on how red dwarf planets evolve. A result ruling out a thick hydrogen atmosphere on TRAPPIST-1e is not the end of habitability. it narrows the possibilities. Science does not move only through dramatic detections. It also moves by closing doors. For the viewer, this actually makes the exoplanet story stronger. Webb is not a wish machine. It is not confirming every hopeful idea. It is testing them. The TRAPPIST-1 system remains fascinating precisely because the answer is not simple. The hot gas giants, meanwhile, show what the telescope can do when the signal is larger. WASP-39b became a chemical demonstration. Carbon dioxide, sulfur dioxide, water, sodium, potassium, and the fingerprints of photochemistry. These worlds are not habitable, but they are laboratories. They teach astronomers how to interpret atmospheric spectra, how clouds and haze complicate transmission, and how stellar radiation drives chemistry. Those skills are exactly what will be needed when smaller and cooler worlds become reachable by future telescopes. The carbon dioxide feature is prominent in Webb's spectral range and relatively easy to detect compared to some other atmospheric species, and CO2 has been subsequently detected in several additional exoplanet atmospheres in Webb's first years of operation. For biosignature detection specifically, oxygen, ozone, methane, nitrous oxide, dimethyl sulfide, and their combinations, Webb can begin to constrain the nearest and most favorable rocky planets around red dwarfs through transmission spectroscopy. But definitive biosignature detection remains beyond any simple single observation claim. It would require many repeated observations, careful separation of stellar activity from planetary atmosphere, and confirmation through independent lines of evidence before any serious claim could be made. Webb's observations of the early universe, galaxies formed within the first billion years after the Big Bang, have been among the most scientifically impactful results of the mission's early operations, and some of the most challenging to interpret. The basic approach is to use the wavelength shifting of cosmic expansion as a distance indicator. The more a galaxy's light is redshifted, the more its wavelengths have been stretched during the light's journey through expanding space, the more distant the galaxy, and the earlier in the universe's history its light was emitted. A galaxy whose light was emitted when the universe was about 400 million years old, roughly 3% of its current age, would have its ultraviolet light shifted by a factor of about 10, arriving at Earth in the near-infrared at roughly 1 to 2 micrometers. Webb's detectors are optimized for exactly these wavelengths, making it the first telescope capable of efficiently studying these earliest galaxies in direct imaging and spectroscopy. The very first galaxies that formed after the Big Bang are expected to show up at the highest redshifts, corresponding to the cosmic dawn and the epoch of reionization, when the first stars began ionicing the surrounding neutral hydrogen gas. In the months following Webb's first science images, analyses of galaxy candidates at these extreme redshifts, photometrically identified from their colors in multiple Webb filter bands, began appearing, with several candidates proposed at redshifts of 10, 11, 12, or even higher, corresponding to the universe at ages of a few hundred million years or less. The confirmation of these redshifts through spectroscopy, actually measuring the wavelengths of emission lines in the galaxy's spectrum to determine the exact shift, followed over the subsequent months as spectroscopic follow-up observations were completed. Several high redshift galaxy candidates were confirmed spectroscopically. GNZ11, previously known from Hubble observations as a strong high redshift candidate, was confirmed by Webb spectroscopy at a redshift of about 11, placing it when the universe was only about 420 million years old. Then the record moved farther still. JADESGS Z140 was confirmed at a redshift of about 14.3, seen less than 300 million years after the Big Bang. And in 2026, Webb pushed the boundary again with MOM Z14, confirmed at a redshift of about 14.4 and seen about 280 million years after the Big Bang. But the scientific story of Webb's early universe observations has been complicated, in a productive way, by galaxies that shouldn't exist, or at least, that shouldn't exist where the models predicted them to be. The standard model of galaxy formation, cold dark matter with hierarchical assembly, in which galaxies grow over time from smaller precursors through mergers and accretion, makes predictions about how massive galaxies should be at different cosmic epochs. The earliest galaxies should be small and relatively low mass, having had less time to accumulate material and form stars. More massive, more evolved galaxies should appear later, as smaller precursors have had time to merge and grow. Webb's early galaxy observations have found several very massive, apparently already evolved galaxies at redshifts higher than expected. A set of candidate galaxies reported in 2022, some of which have subsequently been spectroscopically confirmed, appeared to have stellar masses of roughly 10 billion solar masses at redshifts of 7 to 12, corresponding to times when the universe was only about 500 million to 800 million years old. Assembling that much stellar mass that early requires either very efficient early star formation rates much higher than standard models predict, or scenarios involving more exotic physics. Several possibilities have been invoked to explain these results without abandoning the standard cosmological model. Galaxies in the early universe may simply form stars more efficiently than later populations, concentrating their star formation in shorter, more intense bursts. Stellar populations in early galaxies may have had a different initial mass function, more massive stars per unit mass of star-forming gas, which would produce more stellar light per unit of stellar mass, making the galaxies look more massive in photometric observations than they actually are. Dust may be distributed differently in early galaxies in ways that make photometric mass estimates unreliable. Contamination of the photometric samples by other objects, particularly very bright dust-obscured nearby galaxies or AGN-dominated objects, could artificially inflate the apparent mass of some high redshift candidates. The honest scientific answer at the current state of knowledge is that the early Webb results on massive early galaxies are genuinely surprising relative to pre-launch expectations, and that the implications are still being worked out through more detailed spectroscopic follow-up and improved modeling. Several interpretations are consistent with the data, and the question of whether the standard cosmological model requires modification to accommodate Webb's early galaxy results is genuinely open, pending more comprehensive samples and more careful analysis. What is not in question is that Webb is revealing the early universe in more detail and at greater distances than any previous telescope, and that the picture emerging is richer and more unexpected than the pre-launch predictions anticipated. This is the normal pattern of science at a new frontier. New instruments reveal things that don't quite fit the existing frameworks, and the frameworks are revised, refined, or in rare cases fundamentally rethought. JADESGS Z14-0 and MOM Z14 are important not only because they are distant, but because they are unexpectedly bright. At redshifts above 14, these galaxies are seen when the universe was roughly 2% of its current age. The light reaching Webb left that galaxy before the solar system, before the Milky Way's present structure, before heavy elements had built up through billions of years of stellar generations. And yet the galaxy is not a tiny invisible spark barely forming. It is luminous enough for Webb to study, extended enough to be meaningful, and chemically developed enough to raise questions about how fast early star formation enriched the first galaxies. This does not mean the Big Bang model is broken. That is too strong. It means the details of early galaxy formation are richer than many pre-Webb models expected. Stars may have formed more efficiently in early halos. Feedback may have worked differently in the first galaxies. Dust and gas may have assembled faster. The stellar populations may have been brighter for their mass, or some mass estimates may change as spectroscopy improves. The important thing is the scientific tension. Webb is not simply filling in a textbook picture. It is pressing on the picture and finding where it bends. This is also why record language has to be handled carefully. The most distant known galaxy can change as new observations are confirmed. A record is not the final point on a map. It is the current edge of verified measurement. Webb is now moving that edge often enough that the more durable story is not a single name, but the fact that galaxies at redshift 14 are becoming real physical targets rather than theoretical placeholders. The phrase "beginning of time" is therefore useful as poetry but dangerous as literal science. Webb is not seeing the Big Bang itself. It is not seeing the first instant, or the cosmic microwave background, or the moment space began expanding. It is seeing the first chapters of structure, the time when stars, galaxies, black holes, dust, and heavy elements began building the universe we recognize. Webb's observations of star formation in the Milky Way and nearby galaxies have transformed our ability to see inside the dusty, opaque molecular clouds where stars and planetary systems are born. The key advantage Webb brings to star formation studies is its combination of angular resolution and infrared penetration of dust. Dust absorbs visible and ultraviolet light, hiding the interior of molecular clouds from optical telescopes, but infrared light penetrates dust far more efficiently, allowing Webb's cameras to see inside star-forming clouds in a way that Hubble cannot. The combination of Webb's large mirror, providing high angular resolution even at the longer infrared wavelengths, and its sensitivity allows it to resolve individual protostars and their outflows inside molecular cloud complexes at distances of hundreds to thousands of light years. The Carina Nebula observations, part of the first release images, showed this most dramatically. Dozens of previously unknown protostars emerging from the molecular cloud material in the cosmic cliffs region, visible as compact infrared sources with associated jets. Each of these objects is a star in the process of forming, still embedded in its birth cloud, accreting material, and launching bipolar outflows, a protostellar system potentially forming planetary systems around it. Invisible to previous optical observatories, now revealed in the infrared. Webb's observations of the Orion molecular cloud have provided even more detailed views of the star formation process in the solar system's nearest major star-forming region. Images of the Orion bar, a photodissociation region at the interface between the main Orion nebula and the background molecular cloud, at resolutions achieving scales of less than the diameter of the solar system at Orion's distance, revealed the detailed texture of the cloud material at the ionization front, including individual droplets, small-scale structure in the ionist and neutral material, and jets from embedded young stellar objects that had not been visible in previous observations. The detection of molecular hydrogen emission in photodissociation regions, where the far ultraviolet radiation from massive stars is breaking and exciting molecular gas at the cloud surface, has been a scientifically important aspect of Webb's Orion observations. The emission traces the specific chemistry happening at the boundary between the ionist HII region and the neutral molecular cloud, and the detailed spatial structure of this emission reveals the processes controlling how molecular clouds are eroded by radiation from nearby massive stars, a process fundamental to understanding both star formation and the dispersal of molecular clouds. Webb has also been studying protoplanetary disks, the rotating disks of gas and dust around young stars from which planetary systems form, in new wavelength regimes that reveal their chemical composition and physical structure. Mid-infrared spectroscopy of protoplanetary disks with MIRI has detected water vapor, carbon dioxide, organic molecules, and silicate mineral features in the warm inner regions of disks where rocky planets are assembling, providing the first detailed inventory of the molecular chemistry available to forming terrestrial planets at the time of their assembly. The detection of cold water in the outer regions of protoplanetary disks, water ice in the region analogous to the outer solar system's comet-forming zone, is of particular significance for understanding the water inventory of forming planetary systems. Water delivered to Earth's surface during the heavy bombardment period came from the outer solar system, and understanding how much water is available in the outer regions of forming planetary systems at different stellar types and ages has direct implications for the expected frequency of water delivery to habitable zone rocky planets. The Orion bar is a good example of why high resolution matters. A photodissociation region is not just a line between two zones. It is a layered boundary where ultraviolet radiation changes the chemistry and temperature of gas. Closest to the massive stars, hydrogen is ionized. Farther in, hydrogen becomes neutral. Deeper still, molecules survive. Dust grains are heated. Molecular hydrogen glows. Carbon changes ionization state, and small structures form at scales that older telescopes blurred together. Webb can resolve these layers in ways that connect physical models to actual structure. That is important because the same kind of boundary exists throughout star-forming galaxies. In distant galaxies, these regions are unresolved. They contribute only blended infrared emission. In Orion, Webb can study the process close up, helping astronomers interpret the light of galaxies too distant to resolve. Nearby nebulae therefore become keys to distant galaxies. This is one of Webb's strongest narrative threads. The nearby and the ancient are connected. A star-forming region in our galaxy teaches us how gas turns into stars. That physics helps interpret unresolved star formation in a galaxy near cosmic dawn. A protoplanetary disk nearby teaches us how water and organics are arranged around young stars. That chemistry helps us think about planet formation elsewhere. Webb does not separate local and distant astronomy. It links them through the same infrared physics. Webb has also produced significant results in the study of galaxies across a wide range of cosmic epochs, not just at the extremes of redshift, but through the full history of galaxy formation and evolution. The detailed study of galaxy morphology, how galaxies are shaped, structured, and composed at different cosmic times, has been revolutionized by Webb's combination of resolution and infrared sensitivity. Hubble could image galaxy structure at optical wavelengths in the nearby and moderately distant universe, but at the highest redshifts where the galaxy rest frame ultraviolet is what Hubble sees. The images are dominated by the young, massive stars and star-forming regions that trace ultraviolet emission, providing a potentially misleading picture of the underlying galaxy structure. Webb, seeing the same galaxies in their rest frame near infrared, traces the distribution of older, lower-mass stars, the actual stellar mass distribution, providing a more representative view of the overall galaxy morphology. The contrast between Hubble and Webb views of the same high-redshift galaxies has been striking in some cases. Galaxies that appear clumpy, irregular, and dominated by scattered star-forming regions in Hubble's ultraviolet light can appear as smoother, more organized structures, sometimes showing incipient disk morphology or even spiral structure, in Webb's infrared view, where the overall stellar mass distribution is more faithfully represented. The study of active galactic nuclei, supermassive black holes actively accreting material, has been another important Webb science area. Webb's ability to see through the dust that often surrounds AGN and to detect the infrared emission from dust heated by the AGN rather than by starlight allows it to find AGN in systems where optical surveys might miss them, particularly in dusty, rapidly star-forming galaxies in the early universe. The discovery of unexpected AGN in early galaxies, massive black holes actively accreting in systems where the host galaxy itself appears relatively modest, has contributed to the discussion of how supermassive black holes grow and whether they sometimes grow faster than the surrounding galaxy in the early universe. The first images from Webb's Cosmos Web program, a large survey mapping a relatively wide area of sky in multiple near-infrared filters to build up a statistically meaningful sample of galaxies across cosmic time, began appearing in 2023 and have provided thousands of new galaxy observations ranging from relatively nearby systems to the highest redshift galaxies Webb has detected. This statistical approach, building sample sizes large enough for demographic studies, will ultimately provide the most robust constraints on how galaxy populations evolve through cosmic time, information essential for testing models of galaxy formation and dark matter structure formation. Webb's observations of objects within our own solar system, though perhaps less prominent in public perception than the distant galaxy results, have also produced significant scientific returns. Jupiter has been extensively observed by Webb in multiple wavelength bands, providing global maps of the planet's atmospheric chemistry, temperature structure, and auroral activity in unprecedented detail. Webb's infrared view of Jupiter reveals different atmospheric layers than visible light imaging, providing information about the vertical structure of the atmosphere and the chemistry at altitudes not accessible to visible light instruments. The auroras of Jupiter, powered by the same interaction between the planet's magnetic field and the input of charged particles from Io's volcanic emissions that produces its most intense electromagnetic environment, glow brilliantly in Webb's infrared observations. The Jovian system's moons have also been observed. In 2023, Webb identified carbon dioxide in a specific region on Europa's icy surface, and the analysis indicated that this carbon likely originated in Europa's subsurface ocean rather than being delivered by meteorites or other outside sources. That is not the same as detecting an active plume. In fact, the Webb team looked for plume activity during those observations and did not detect it, while noting that Europa's plumes, if present, may be variable. The result was still important because it connected surface chemistry to the ocean world question. Material from Europa's interior may be reaching the surface in ways Webb can detect spectroscopically. Saturn and its ring system have been observed, with particular attention to seasonal changes in Saturn's atmosphere and to the chemical composition of the ring material in mid-infrared wavelengths where the ring's spectral features had not previously been well characterized. The detection of specific silicate and water ice features in Saturn's rings provides information about the composition and processing history of the ring material. Mars has been observed at multiple points in its orbit, providing thermal maps of the Martian surface and atmosphere at mid-infrared wavelengths. Spectroscopy of atmospheric gases, including carbon dioxide and dust, and information about the temperature distribution of the surface and lower atmosphere. Webb's observations complement ongoing monitoring by Mars orbiters and provide a different perspective, a more distant, global view, from which some atmospheric features are better characterized. Webb's solar system work is a useful reminder that a telescope designed for the early universe can also study nearby worlds. This might seem surprising. Webb is extremely sensitive, and many solar system objects are bright. Pointing at Mars or Jupiter is not like pointing at a faint galaxy near cosmic dawn. Observations have to be planned carefully to avoid saturating detectors, to track moving targets, and to account for Webb's pointing and sunshield constraints. But when used correctly, Webb can measure infrared spectra and temperatures in ways that complement orbiters and flyby missions. For icy moons, this is especially valuable. A spacecraft flyby gives close detail, but only at one place in time. A telescope like Webb can monitor objects repeatedly, search for changes, and identify chemical signatures across larger regions. It cannot replace Europa Clipper, JUICE, or future landers. It can help choose questions for them. The Europa carbon dioxide result is a perfect example. It is not a photograph of an ocean. It is not proof of life. It is a chemical clue on a frozen surface, interpreted in the context of geology and ocean world models. That kind of clue is exactly what infrared astronomy is good at, not giving a simple answer, but narrowing the possibilities. Webb's study of stellar endpoints, white dwarfs, neutron stars, and their associated nebulae has provided detailed characterizations of these objects and their environments that previous infrared capabilities could not match. The detailed images of planetary nebulae mentioned in the nebulae episode, the Ring Nebula, the Southern Ring Nebula, and others, demonstrate Webb's ability to see through the dust in these objects to the inner structures previously hidden, and to characterize the chemistry of the ejected material in a spectral range where the most diagnostic molecular features appear. Infrared spectroscopy of planetary nebulae traces molecular species, including H2, CO, and a range of carbon-based molecules that probe the nucleosynthetic history of the central star, what elements the star synthesized during its lifetime, and how efficiently it returned them to the interstellar medium. Supernova 1987A, the closest observed supernova in 4 centuries, in the Large Magellanic Cloud, has been a priority Webb target. The Webb mid-infrared images of SN 1987A, released in 2023, revealed the inner ring of the remnant in detail unprecedented at these wavelengths, showing the complex structure of the growing shock wave interacting with the pre-existing circumstellar ring and the distribution of dust forming in the cold, expanding ejecta. The detection of argon and sulfur emission in the inner remnant, material produced by the explosive nucleosynthesis in the supernova's core, represents the first time these specific elements have been detected in SN 1987A's ejecta, providing direct evidence of the nuclear burning products of the explosion. The future of Webb is still being written. The telescope was launched with enough fuel for a nominal 10-year science mission, and because the launch was so precise, the Ariane 5's trajectory was accurate enough that the spacecraft needed very little propellant for the trajectory correction maneuvers planned for the journey to L2. The fuel reserves are sufficient to support science operations well beyond 10 years, potentially 20 or more. Webb will not be limited by fuel in its operational lifetime. It will eventually be limited by the gradual degradation of its instruments or by some mechanical or electronic failure. But neither of these is predictable and neither is necessarily imminent. The science programs already approved for the first several years fill Webb's time with a combination of directors' discretionary early release science programs, guaranteed time observations for the teams that built the instruments, and general observer programs selected through competitive peer review from the broader astronomical community. The GEO programs span an enormous range of science, solar system targets from Mars to Oort cloud objects, young stellar objects and protoplanetary disks, exoplanet atmospheres at various sizes and temperatures, nearby galaxies in detail, distant galaxy populations at intermediate and high redshifts, AGN and their host galaxies, galaxy clusters and their lensing effects, and the highest redshift galaxies near the cosmic dawn. The science themes that seem most likely to dominate Webb's legacy, based on the first few years of operation, are the early universe galaxy population and the exoplanet atmospheric characterization program. The early universe results are already challenging models in ways that are scientifically productive, and continued spectroscopic follow-up of high redshift galaxy candidates will either confirm or refute the most surprising apparent discoveries. The exoplanet program is advancing toward the biosignature detection regime for the most favorable red dwarf systems, with TRAPPIST-1 remaining the highest priority long-term program. There is also the prospect of discoveries that cannot be anticipated from where we currently stand. Every major new observatory in the history of astronomy has found things that no one was looking for, phenomena unknown before the telescope revealed them, categories of object that required entirely new theoretical frameworks, questions that transformed the field in ways the pre-launch planning documents could not have specified. Webb will be no exception. The universe is more complex than our current models, and a telescope that sees farther and more clearly than any before it will find complexity we don't yet know about. Webb's future will probably be defined by accumulation as much as by surprise. The first image of a distant galaxy is exciting. The 1000th redshift confirmation is what changes statistics. One exoplanet spectrum is a breakthrough. Dozens of spectra across many planet types become atmospheric demographics. A single protoplanetary disk shows chemistry. A survey of disks tells astronomers how common that chemistry is and how it changes with stellar type and age. This is how a great observatory builds a legacy, not only by producing iconic images, but by creating samples large enough for patterns to emerge. Webb will also work alongside other observatories. Hubble continues to provide ultraviolet and visible context. Chandra provides X-rays. ALMA maps cold gas at millimeter wavelengths. Roman, when operating, will survey wide fields in infrared. Ground-based extremely large telescopes will bring enormous light, gathering power and adaptive optics. Webb is not a replacement for all astronomy. It is a central instrument in a larger ecosystem. The universe is too broad for one telescope, even one as powerful as Webb. Before we move toward the final reflection, it is worth holding Webb's major discoveries as one connected story rather than a list. A list can make the telescope feel scattered. One paragraph about exoplanets, one about distant galaxies, one about nebulae, one about Jupiter, one about dying stars. But Webb is coherent because all of these subjects are connected by the same physical problem. Light carries information, and some of the most important information in the universe is hidden in infrared light. A young galaxy near cosmic dawn is infrared because the universe has stretched its light. A planet's atmosphere is readable in infrared because molecules absorb at specific wavelengths. A protostar is visible in infrared because dust hides it in visible light but glows when warmed. A planetary nebula reveals molecules and dust in infrared because stellar death leaves behind material too cool or too obscured for optical light alone. A moon like Europa can be studied in infrared because surface compounds leave spectral fingerprints. That is Webb's unity. It does not study one kind of object. It studies the hidden fingerprints of matter. This also helps explain why Webb's discoveries can feel subtle even when they are enormous. A spectrum does not always look as dramatic as a photograph. A small bump in a line between 4 and 5 micrometers may not look emotional, but that bump can be the first clear detection of carbon dioxide in an exoplanet atmosphere. A faint red smudge in a deep field may not look grand, but it can be a galaxy seen when the universe was only a few 100 million years old. A few infrared pixels on Europa may not look like much, but they can connect surface carbon dioxide to a subsurface ocean. Modern astronomy often asks the viewer to trust small signals. Webb is a telescope that turns those small signals into entire stories. The story of the early universe is one of those stories. After the Big Bang, the universe was hot, dense, and opaque. For hundreds of thousands of years, light could not travel freely because electrons and nuclei were mixed in a plasma that scattered photons constantly. When the universe cooled enough for electrons and nuclei to combine into neutral atoms, light was finally able to travel. That ancient light, is what we now see as the cosmic microwave background. Webb does not observe the cosmic microwave background directly. That belongs to microwave observatories like COBE, WMAP, and Planck. After that came the cosmic dark ages, a period before the first stars and galaxies had filled the universe with starlight. Matter was not empty. Hydrogen and helium were present. Dark matter provided gravitational scaffolding. Small variations in density grew slowly under gravity. But there were not yet stars in the ordinary sense. And without stars, there were no galaxies glowing across space. Then the first stars formed. Those first stars, sometimes called population 3 stars, have not yet been directly observed. They are expected to have formed from nearly pristine hydrogen and helium, with little or no heavy elements. Without heavier elements to cool gas efficiently, they may have been very massive, very hot, and very short-lived. They would have changed their surroundings dramatically, producing ultraviolet radiation, exploding as supernovae, and seeding the universe with the first heavy elements. Webb is not simply photographing those first stars one by one. That may be beyond its reach in most cases. But it is observing the early galaxies that formed in the era when the first generations of stars were lighting up the universe. It is measuring how quickly galaxies became bright, how fast they formed stars, how early heavy elements appeared, and how the neutral hydrogen between galaxies became ionized. This process is called reionization. Reionization is one of the most important transitions in cosmic history. The early universe became neutral after the cosmic microwave background was released. Later, ultraviolet light from the first stars and galaxies stripped electrons from hydrogen again, ionizing the intergalactic medium. By the end of reionization, the universe had become more transparent to ultraviolet light. The fog lifted. The question is how it happened. Were small galaxies the main drivers? Were early black holes important? How quickly did ionizing radiation escape from galaxies into intergalactic space? How clumpy was the process? Did it happen gradually everywhere or patch by patch, bubble by bubble, around early galaxy groups? Webb helps because it can find and study the galaxies that existed during this transition. It can measure their brightness, sizes, star formation rates, and spectra. It can look for emission lines that reveal ionized gas and chemical enrichment. It can test whether early galaxies were numerous and bright enough to reionize the universe. This is why the high redshift galaxy story is not only a race for the most distant object. Record-breaking galaxies get headlines, but the larger science is demographic. Astronomers need samples, many galaxies, confirmed redshifts, different environments, different brightness levels, different masses. A single galaxy can surprise. A population can change a model. JADESGS Z14-0 and MOM Z14 matter because they extend the known frontier. But Webb's deeper legacy may come from the full statistical picture of galaxies between redshifts 6 and 15. How common they are, how luminous they are, how much dust they contain, how chemically mature they are, and how their black holes grew. The distant universe is not only far away, it is young. Webb is watching childhood photographs of cosmic structure. The exoplanet story is quieter, but just as important. For centuries, planets outside the solar system were speculation. Then, in the 1990s and 2000s, they became discoveries. Hot Jupiters, super-Earths, mini-Neptunes, compact multi-planet systems, worlds orbiting red dwarfs, worlds on eccentric orbits, worlds unlike anything in our solar system. The first stage of exoplanet science was simply finding them. The second stage was counting them. Webb belongs to the third stage, beginning to understand what some of them are like. A transiting exoplanet gives astronomers a special opportunity. When the planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere, if it has one. Molecules in that atmosphere absorb particular wavelengths. By comparing the starlight during transit with the starlight outside transit, astronomers can infer atmospheric composition. The principle is simple. The execution is extremely difficult. The signal is small. The star is bright. The planet is faint. Instruments must be stable. Stellar activity must be modeled. Clouds and haze can mute molecular features. Different atmospheric compositions can sometimes produce similar spectra. A measurement that looks like a molecule might be affected by the star's surface, the planet's clouds, or instrument systematics. This is why serious exoplanet atmosphere work moves carefully. Webb's strength is that it can obtain spectra with a clarity that earlier instruments often could not reach. WASP-39b became a showcase because it is large, hot, and favorable for atmospheric transmission spectroscopy. Its atmosphere revealed carbon dioxide clearly, and later observations built a broader chemical picture, including photochemistry. WASP-96b, in the first release, showed water vapor and clouds or haze. These planets are not Earth-like, but they are training grounds for interpreting atmospheres. Rocky worlds are harder. The TRAPPIST-1 system is the most famous because it contains 7 Earth-sized planets around a nearby red dwarf. The planets are small and close to their star, which makes their transits frequent and measurable. Several receive amounts of energy that place them in or near the region where liquid water might be possible if they have suitable atmospheres. That phrase matters. If they have suitable atmospheres. A planet's orbit alone does not make it habitable. The early Webb results have been cautious. TRAPPIST-1b likely lacks a substantial atmosphere. TRAPPIST-1c appears unlikely to have a thick carbon dioxide atmosphere. TRAPPIST-1d and E remain more open, but have had thick hydrogen atmospheres ruled out. The stellar activity of TRAPPIST-1 makes the analysis more difficult because spots and flares on the star can contaminate the planetary signal. The system remains a priority because it is still one of the best laboratories available, not because it has delivered an easy answer. This is valuable for viewers to understand. Science is not disappointing when it becomes more complicated. It becomes more real. The search for biosignatures is even more delicate. Oxygen alone would not be enough. Methane alone would not be enough. A living planet would have to be interpreted as a system. Star type, atmospheric composition, surface environment, geological context, photochemistry, and false positive pathways. Webb may help constrain some nearby worlds, but a confident biosignature detection will likely require future telescopes designed specifically for that purpose. So Webb's exoplanet legacy may not be a single headline saying life has been found. It may be something more foundational, showing which kinds of atmospheres are common, which planets lose them, how red dwarf activity changes habitability, how clouds and chemistry shape spectra, and what future life search telescopes need to measure. That is slower, but it is deeper. Webb's view of star formation gives the telescope a more intimate scale. The early universe is enormous and remote. Exoplanet atmospheres are subtle and statistical, but star-forming regions have a different feeling. They are places where structure is visibly emerging from darkness. A cloud that looked like a wall becomes a nursery. A dark patch becomes a cluster of hidden sources. A jet appears where a young star is throwing material back into the cloud from which it is still forming. This is what made the Carina Cosmic Cliffs image so effective. It looked like a landscape, but it was not a landscape. The apparent mountains and valleys were the edge of a molecular cloud being carved by radiation from young stars. The steam above the ridge was hot gas and dust being photoevaporated. The red points and streaks were young stars and jets. Webb turned an image that could have been merely pretty into a diagram of star birth and stellar feedback. Feedback is one of the key ideas in modern astrophysics. Stars are born from clouds, but the most massive stars begin destroying the clouds almost immediately. Their ultraviolet radiation ionizes gas. Their winds push material outward. Their future supernovae send shock waves through surrounding space. This can end star formation by dispersing gas. It can also trigger new star formation by compressing nearby material. The same star can be creator and destroyer. Webb is useful here because young stars are often hidden behind dust. Hubble can see the illuminated surface. Webb can see deeper, into the warm dust and embedded sources. This is not a replacement of one telescope by another. It is a layered view. Hubble shows the optical face. Webb shows the infrared interior. The pillars of creation are another example. Hubble made the pillars famous in 1995, showing towering columns of gas and dust in the Eagle Nebula. Webb returned to them and revealed young stars embedded inside and around the pillars, with infrared light penetrating dust that visible light could not. The story changed from 3 dramatic columns to a more complete picture, dense gas being eroded by nearby massive stars, while new stars form within it. The Horsehead Nebula, the Orion Bar, and the Ring Nebula show the same principle in different forms. Webb revisits famous objects not because astronomers have run out of new targets, but because a famous object can still contain hidden physics. A telescope does not have to discover a new object to make a new discovery. Sometimes it changes the meaning of an object everyone thought they already knew. Protoplanetary disks are one of Webb's most important long-term targets in this area. A disk around a young star is the place where planets begin. Dust grains grow. Ices freeze beyond snow lines. Organic molecules form, survive, migrate, or break apart. Water vapor appears in warm inner regions or is transported from colder outer regions. Silicates reveal mineral processing. Carbon dioxide and hydrocarbons trace chemistry. The disk is not a simple flat pancake. It is a chemical and dynamical environment where future planets inherit their starting materials. Webb's infrared spectrographs can detect molecules in these disks, including water, carbon dioxide, organic molecules, and silicate features. That means it can help answer questions that connect directly to our own origin. How common is water in planet-forming disks? Does it reach the inner regions where rocky planets assemble? How does chemistry differ around sun like stars and low-mass stars? Do disks around small red dwarfs have the same ingredients available for terrestrial planets? These questions are not answered by one observation. They require many disks at different ages and around different stars. But Webb has made the chemistry of planet formation more observable than before. In a sleep-friendly story, this section gives warmth to the telescope. Webb is not only looking backward toward cosmic dawn, it is also looking at the places where future solar systems begin. Webb also changes how familiar solar system objects are seen. This can sound surprising because Webb was not built as a planetary flyby mission. It does not skim past a moon. It does not orbit Mars. It does not dive through Saturn's rings. It sits near L2 and looks from far away. But distance is not the same as irrelevance. A powerful infrared telescope can study temperature, composition, auroras, clouds, rings, and surface ices in ways that spacecraft in other locations cannot always provide. Jupiter in Webb's infrared view is not the Jupiter of ordinary visible photographs. Its auroras glow. High-altitude haze appears differently. Storms, rings, and small moons can be seen in the same system. Webb can look at Jupiter as a world of heat, chemistry, and magnetic interaction, not only as a striped planet. Saturn's rings and atmosphere become laboratories for seasonal change and icy material. Uranus and Neptune, still visited only once each by Voyager 2, are especially valuable targets for remote telescopes. Webb can monitor them at wavelengths unavailable to Voyager, track clouds and thermal structure, and help prepare the case for future ice giant missions. Mars, too, is useful despite being bright and close. Webb observes it carefully to avoid saturation, but its infrared spectra provide global information about atmospheric gases, dust, clouds, and surface temperature. It complements orbiters rather than competing with them. The Europa carbon dioxide detection is one of the clearest examples of Webb's solar system value. Europa is already famous because its subsurface ocean may be in contact with a rocky seafloor, making it one of the most important astrobiology targets in the solar system. Webb did not see the ocean. It did not detect life. It identified carbon dioxide concentrated in a specific region of the surface, likely connected to material from the ocean or interior. That is a subtle result, but subtle is not weak. A surface chemical clue can guide future missions toward the most interesting regions. This is a good way to explain Webb to a viewer. The telescope is not only about distance. It is about wavelengths. Sometimes the most important hidden thing is 13 billion light-years away. Sometimes it is on the surface of a moon in our own solar system. The same instrument family can touch both scales. The study of dying stars gives Webb another emotional and scientific layer. A planetary nebula is not a planet-forming cloud. It is the glowing shell of material shed by a dying star, similar in broad category to the future sun. Hubble showed many of these objects in visible light with extraordinary beauty. Webb sees deeper into dust and molecules, revealing structures that optical light can hide. The Southern Ring Nebula, one of Webb's first images, is a perfect example. In visible-style images, it looks like a glowing shell around a dying star. In Webb's mid-infrared view, the dusty companion and the complicated history of ejection become clearer. Rings and shells show that the star did not simply breathe out material once. It lost mass in episodes. A companion star likely shaped the outflow. The nebula becomes not only a death scene, but a record of stellar interaction. The Ring Nebula, revisited by Webb, revealed fine structure, knots, arcs, and molecular material in new detail. It was already famous. Webb made it more physically layered. The image becomes a record of how a star returns carbon, nitrogen, dust, and molecules to interstellar space. Supernova remnants give the violent version of that same return. Cassiopeia A is one of the youngest known supernova remnants in the Milky Way. Webb's infrared observations revealed structures in dust and ejecta that help astronomers understand how massive stars explode and how newly formed elements and grains are distributed into space. A supernova remnant is not only debris. It is a chemical delivery system, a shock wave, a dust factory, and sometimes a dust destroyer. Supernova 1987A, in the Large Magellanic Cloud, is another case where Webb adds to decades of observation. Since 1987, astronomers have watched the remnant evolve almost in real time by cosmic standards. Webb can see warm dust and emission from material in ways that complement Hubble, Chandra, and ALMA. Together, these observatories show a stellar death becoming a remnant. This matters because the story of Webb would be incomplete if it only looked at beginnings. The telescope studies beginnings and endings, galaxies forming, stars forming, planets forming, stars dying, dust returning, chemistry cycling. The universe is not a straight line from simple to complex. It is a circulation of matter, and Webb sees many points in that circulation. There is also a quieter part of Webb's story, the way data becomes knowledge. A public image may be released as a finished object, balanced, colored, labeled, ready for news articles and screens. But before that image exists, there are raw detector readings, calibrations, background corrections, cosmic ray removal, flat fields, wavelength solutions, pointing models, and careful choices about which filters or spectral ranges are being combined. A telescope does not hand humanity a conclusion. It hands humanity data. For spectra, the process is even less intuitive to the public. Webb may observe a planet during a transit, but the result is not a photograph of the planet's atmosphere. It is a change in starlight as a function of wavelength. Scientists compare that change to models. They ask which molecules can produce the observed pattern, how clouds alter it, how stellar activity contaminates it, how instrument noise behaves, and how many transits are needed before the signal can be trusted. For distant galaxies, a faint red object in an image may first be a candidate. Its colors suggest a high redshift because it disappears in shorter wavelength filters and appears in longer wavelength filters. But photometric redshifts can be wrong. Dusty lower redshift galaxies can mimic some colors of very distant galaxies. Strong emission lines can affect brightness in certain filters. Spectroscopy is needed to confirm the distance, and even then the interpretation of mass, age, and star formation history depends on models. This is why Webb's first years have included both excitement and caution. The telescope finds candidates quickly. Science confirms them slowly. The most careful results are often less dramatic than the first headlines, but more durable. That distinction makes the script stronger for an adult audience. We do not need to pretend every Webb discovery instantly overturns cosmology. The more interesting truth is that Webb is producing data good enough to make scientists argue seriously. It is sharpening the questions. A new telescope does not end uncertainty. It improves the quality of uncertainty. The engineering story remains present even after the science begins. Webb's mirror is exposed to space. Tiny micrometeoroids cross the solar system constantly, and a few have struck mirror segments. This was expected. A large mirror in space is a large target. The segments were designed with margins, and the telescope's wavefront can be adjusted to compensate for small changes. Still, each impact is a reminder that Webb is not a protected museum object. It is an operating machine in a real environment. The sunshield, too, is not only a symbol. It is the reason the telescope can do infrared astronomy. 5 thin layers of captons separate the hot side from the cold side. Each layer is thinner than the whole shield appears in photographs, and the spacing between layers lets heat radiate sideways and outward. The shield is not a thick blanket. It is a carefully shaped thermal architecture. The cryocooler for Miri is another quiet marvel. Most of Webb's instruments cool passively, but Miri needs to be colder than the rest of the observatory. Its cooler moves heat from the instrument to the warm side of the spacecraft through a long system designed to avoid vibration and preserve instrument stability. The result is a mid-infrared camera and spectrograph cold enough to detect faint thermal signals from the universe instead of its own warmth. The gold on the mirror is also functional, not decorative. Gold reflects infrared light extremely well. The layer is very thin, laid over beryllium segments that keep their shape at cryogenic temperatures. The famous golden mirror looks luxurious, but its appearance is a consequence of physics. This is one reason Webb works so well for a sleep science channel. The machine itself is calm in operation but dramatic in design. Nothing moves quickly now. It points, waits, gathers photons, and sends data. But behind that stillness is a history of folding, cooling, aligning, shielding, and surviving. Another useful way to understand Webb is to compare it with Hubble without turning the comparison into a contest. Hubble changed astronomy because it gave the universe a sharp, visible face above Earth's atmosphere. It saw galaxies in optical detail, watched planets, measured cosmic expansion, revealed deep fields, and became part of public culture. Webb did not make Hubble obsolete. It extended the story into wavelengths Hubble could not cover with the same power. A Hubble image of a nebula can show glowing ionized gas, dark dust lanes, and reflected starlight. A Webb image can show embedded stars, warm dust, molecular emission, and structures hidden behind the dust. A Hubble deep field shows galaxies through visible and near-infrared light. A Webb deep field reaches deeper into the infrared and farther into redshifted early light. Hubble and Webb are not enemies. They are complementary eyes. This is also true of Chandra, Spitzer, Herschel, Alma, and future Roman. X-rays reveal hot gas around black holes and supernova remnants. Millimeter observations reveal cold molecular gas. Infrared sees dust, molecules, and ancient redshifted light. Ultraviolet sees hot stars and ionized gas. The full universe is multi-wavelength. The public often sees a single final image. Astronomers see layers. A galaxy cluster, for example, can be studied in visible light for its galaxies, infrared light for old stars, and high redshift background galaxies, X-rays for hot intercluster gas, and gravitational lensing for the dark matter distribution. The same object becomes 4 different maps. Webb adds one of the most important maps, but it does not erase the others. This helps keep the script honest. Webb is extraordinary because of what it adds, not because everything before it was insufficient. Hubble made Webb scientifically necessary by showing what could be done and where the next frontier lay. Gravitational lensing is one of Webb's most useful natural tools. A massive galaxy cluster bends space-time around it. Light from galaxies behind the cluster follows that curved geometry, and to us those background galaxies can appear distorted, stretched into arcs, multiplied into several images, or magnified beyond what the telescope could see alone. The cluster becomes a natural lens. This is what made Webb's first deep field, SMACS 723, so powerful. The telescope was not only looking at a cluster, it was using the cluster to look beyond itself. The galaxies in the foreground were part of the subject, but they were also part of the instrument. Their gravity amplified more distant galaxies behind them. This is a beautiful idea. The universe supplies some of its own optics. Gravitational lensing lets Webb study galaxies that would otherwise be too faint. It also lets astronomers map dark matter in clusters, because the lensing pattern depends on the total mass distribution, not only on the visible galaxies. When a cluster bends light, it reveals the mass that light alone might miss. The same principle can help study individual distant stars or compact objects if a lensing alignment is strong enough. Webb's sensitivity makes some of these rare alignments scientifically valuable. A telescope built by humans and a lens built by gravity can work together. This also gives the early universe story a slightly humbling quality. We do not see the deepest universe by engineering alone. We also depend on cosmic geometry, massive clusters in the right places, background galaxies behind them, and light paths bent across billions of years. Webb's black hole science is another part of the early universe puzzle. Almost every large galaxy in the modern universe appears to contain a supermassive black hole at its center. Some are quiet, like the black hole at the center of the Milky Way most of the time. Some are active, feeding on gas and dust, heating surrounding material, and shining across the electromagnetic spectrum. These active galactic nuclei can outshine their host galaxies. The mystery is how such massive black holes grew so early. Webb has found active black holes in young galaxies and has helped reveal systems where black hole growth and galaxy growth may not proceed in the simple order once imagined. Did the first black holes begin as remnants of the first massive stars? Did some form by direct collapse of gas clouds? How quickly can they feed before radiation pressure pushes material away? How do they influence early star formation? Infrared observations are important because black holes often hide behind dust. The material falling toward the black hole heats dust, and that dust glows in infrared. Webb can detect some of these buried active nuclei and separate their light from stellar light in the host galaxy. This matters for the apparent too massive, too early galaxy problem. If a galaxy's light is partly powered by an active black hole rather than only by stars, estimates of stellar mass can change. If early black holes are common, they may help explain some of Webb's surprising objects. But they also introduce new questions. How did the black holes themselves grow so quickly? Again, Webb does not give a single simple answer. It sharpens the contradiction in a useful way. Large Webb surveys may become less famous than single images, but they are scientifically essential. A single deep image can show what the telescope can do. A survey shows what the universe generally does. Programs like JADES, CEERS, Cosmos Web, and other large observing campaigns build samples of galaxies across cosmic time. They allow astronomers to ask demographic questions. How many galaxies exist at a given redshift? How massive they are? How quickly they form stars? How dusty they are? How often they host active black holes? And how their shapes change over time. This statistical side of astronomy is easy to understate because it is not as visually dramatic. But it is the difference between saying, "We found a strange galaxy," and saying, "This kind of galaxy is common." The first is discovery. The second is understanding. Surveys also protect against overinterpretation. Early candidates can be exciting, but a candidate can be wrong. A larger sample with spectroscopy and careful modeling tells astronomers which surprises are real patterns and which are rare outliers or selection effects. Webb's first years produced both genuine surprises and revised claims. That is exactly how a frontier instrument should work. For the listener, this can be made simple. Webb is not only taking portraits. It is building a census. It is counting the young universe. There is one wording issue that deserves care. Webb does not see the beginning of time. That phrase is useful for a title because it gives the viewer a clear emotional direction. But inside the science, the wording should be refined. The beginning of time. If that phrase means the Big Bang itself or the first instant of cosmic expansion, is not something Webb can directly observe. The earliest directly observed light in the universe is the cosmic microwave background, released about 380,000 years after the Big Bang, and it is seen in microwave wavelengths, not by Webb. Webb looks later than that. It looks into the era when the first galaxies and black holes were forming, when starlight began transforming the universe from a dark, neutral medium into a transparent, ionized one. That is still extraordinarily early. A galaxy seen 290 million years after the Big Bang is ancient light by any human scale. But it is not the first moment. This distinction actually makes the script more trustworthy. It keeps the poetic title while giving the listener the accurate meaning. Webb lets us see toward the beginning of cosmic structure, not the literal beginning of time. A good science script can use wonder without exaggeration. Webb does not need exaggeration. The real facts are already large enough. The emotional strength of Webb is different from the emotional strength of Voyager. Voyager moves outward. Its story is distance, endurance, and a signal fading into interstellar dark. Webb does not travel away in that way. It stays near Earth, in a controlled orbit around L2, protected by geometry and shadow. Its story is not the journey of a spacecraft into the unknown, but the stillness of an observatory built to receive. That stillness is powerful. Webb points at a patch of sky and waits. Photons that have crossed billions of years fall onto gold-coated mirrors. They reflect into instruments colder than almost anything naturally experienced on Earth. They become electrical signals, then data, then calibrated measurements, then human understanding. A telescope is a patient machine. It does not chase the early universe. It lets the early universe arrive. This is a good feeling for the end of a sleep episode. The telescope is not dramatic once it is working. It is quiet, cold, and steady. But what reaches it is enormous. Ancient galaxies, hidden stars, planetary atmospheres, dying suns, and the infrared traces of chemistry across space. The contrast is beautiful, a calm machine receiving violent, ancient, distant light. The public story of Webb also includes risk, and that risk should not be forgotten after success. Before launch, Webb was sometimes described as a mission with hundreds of single-point failures. That phrase can be misunderstood, but the fear behind it was real. A single deployment problem in the wrong place could have limited or ended the mission. The sunshield had to unfold. The tensioning system had to work. The mirror wings had to swing into position. The secondary mirror had to deploy and hold precise alignment. The spacecraft had to perform trajectory burns correctly. The instruments had to cool. The cryocooler had to operate. The segmented mirror had to become one optical surface. There was no shuttle servicing mission waiting. This is why the early weeks after launch were so tense for the mission team. The telescope was not safe simply because the rocket had worked. It had to survive a long sequence of transformations. Every day, a new part of the observatory became real. The success also changed the tone of public memory. Before launch, Webb was often discussed as over budget, delayed, and risky. After launch, the same long development history began to look like preparation rather than failure. That does not erase the cost or the delays. It gives them context. Some machines are difficult because the goal is genuinely difficult. A 6.5-meter cryogenic infrared telescope at L2, folded for launch and unfolded in space, was not a routine project. It was a generational bet. The bet paid off. That fact is satisfying, but it should not make the difficulty invisible. The beauty of Webb's images is built on years of engineering caution, testing, redesign, and patience. Every spectacular galaxy field rests on a deployment that could have failed. Every exoplanet spectrum rests on a sunshield that opened. Every early universe result rests on mirror segments that aligned to nanometer precision. The science is the visible reward. The engineering is the hidden foundation. A telescope like Webb also changes the relationship between professionals and the public. Many scientific instruments produce results that are powerful but visually abstract. Particle detectors, gravitational wave interferometers, neutrino observatories, and radio arrays often require specialized plots to communicate their discoveries. Webb does produce spectra and abstract data, but it also produces images that immediately invite attention. A person can look at the Carina Nebula, the Pillars of Creation, or a deep field and feel the scale before understanding the measurements. That visual access matters. It gives the public a first emotional connection, and then the science can enter through explanation. The image becomes a doorway. Why is this galaxy red? Why are these arcs curved? Why is the nebula glowing? Why are the stars surrounded by diffraction spikes? Why does infrared reveal more background galaxies than visible light? This is especially important for a channel like Space for Sleep. The viewer may not arrive wanting a technical lecture. They may arrive wanting something calm, beautiful, and intelligent. Webb gives exactly that combination. The images are peaceful to look at, but behind them are ideas deep enough to sustain a long episode. The diffraction spikes around bright stars are a good example. They are not cosmic rays or beams coming from the stars. They are optical patterns caused by the geometry of Webb's segmented mirror and support structures. The 8-pointed star shapes in Webb images are a signature of the telescope itself. The universe is being filtered through the instrument's design. Every telescope leaves a fingerprint on what it sees. Webb's fingerprint has already become part of the visual language of 21st century astronomy. The public now recognizes the gold mirror, the cold sunshield, the deep red galaxies, the infrared nebulae, and the 8-pointed stars. This recognition is not trivial. It means the telescope has entered culture as Hubble did before it. Science becomes stronger when people can remember its images. The question of lifetime adds another layer of quiet suspense. Webb was planned for a minimum science mission of about 5 years, with a goal of 10 years or more. The precision of the Ariane 5 launch preserved more fuel than expected, making a longer mission possible. Fuel matters because Webb must perform station keeping near L2 and manage momentum through occasional maneuvers. If fuel lasts, the telescope can keep operating as long as the instruments and spacecraft systems remain healthy. But no space telescope lasts forever. Detectors age. Electronics can fail. Micrometeoroids continue to strike. Thermal systems must remain stable. Reaction wheels and communication systems must keep working. The future is promising, but not guaranteed. That uncertainty makes Webb's current years precious. The telescope is operating now with extraordinary sensitivity, while its instruments are healthy and its mirror is aligned. Every observing cycle matters. Every approved program is a use of finite time. Astronomers compete for Webb time through peer review because the demand is far greater than the available hours. A proposal must justify why the observation matters, why Webb is needed, which instrument mode should be used, how much exposure time is required, and what scientific question will be answered. Behind every beautiful public release image are many other observations that may never become famous, but may be essential to a field. This is another way Webb resembles a great observatory on Earth, but with higher stakes. Telescope time is always limited. Webb time is uniquely limited because no identical instrument exists elsewhere. The telescope's future legacy will be shaped by thousands of such choices. One of Webb's most important effects is that it changes what feels normal. Before Webb, a galaxy from the first few 100 million years of cosmic history was an extreme target. A handful of candidates could dominate discussion. Now, high redshift candidates appear in survey fields with enough frequency that astronomers can compare populations. Before Webb, detailed infrared spectra of exoplanet atmospheres were possible only in limited cases. Now, hot gas giants are becoming chemical laboratories. Before Webb, some star-forming regions were famous for their optical surfaces. Now, their embedded interiors are part of the public view. This is how scientific revolutions often feel after they begin. The extraordinary becomes a data set. That does not make it less extraordinary. It means the frontier has moved. The first deep field showed what Webb could do. Later surveys turned that capability into routine pressure on models. The first exoplanet spectra proved the sensitivity. Later programs turned spectra into comparisons. The first images of nebulae stunned the public. Later observations let scientists measure structure, chemistry, and evolution. The greatest observatories do not only answer questions. They change which questions can be asked every day. There is also a philosophical shift in Webb's work that is easy to overlook. For a long time, people imagined the distant universe as simply smaller, younger, and less developed. That is partly true. Early galaxies had less time to grow. Heavy elements had less time to accumulate. Dust had less time to form. But Webb shows that young does not mean simple. The early universe was already capable of intense star formation, rapid enrichment, black hole growth, and structures bright enough to challenge expectations. The same is true for small planets and moons. A small rocky planet around a red dwarf is not automatically Earth-like. A cold icy moon is not automatically inert. A protoplanetary disk is not a smooth ring of dust waiting passively to become planets. A planetary nebula is not a simple shell. Everywhere Webb looks, simple categories become physical systems. This is the deeper pattern of the telescope's discoveries. Complexity appears earlier, colder, smaller, dustier, and farther away than simple intuition expects. That pattern is good for storytelling because it gives the episode a repeated emotional turn. The viewer expects one thing. Webb reveals more. A first galaxy is not merely faint. It is bright enough to force questions. A planet atmosphere is not just detected, it is chemically active. A nebula is not just beautiful, it is a star-forming interface. A moon's surface is not just ice. It may carry chemistry from an ocean below. A dying star is not a simple ring. It is a record of mass loss and companions. Again and again, Webb turns a picture into a process. This is also why Webb's strongest discoveries are not always the easiest to summarize. A headline wants a clean sentence. The oldest galaxy, the first carbon dioxide, a planet with no atmosphere, a hidden star, a dying star, a record-breaking image. But the science behind the headline is usually conditional and layered. The most distant galaxy is current, not eternal. A first detection depends on instrument mode and confidence level. A non-detection rules out some atmospheres, but not all. A spectrum points to chemistry, but must be checked against models. A beautiful nebula image reveals structure, but the physical interpretation may take years. Good science communication has to keep the wonder while preserving the caution. That is one reason Webb is ideal for a calm format. The story does not need to shout. It can let the scale do the work. A photon leaves a young galaxy before the sun exists, crosses expanding space for more than 13 billion years, enters a cold telescope near L2, hits a gold-coated mirror, is measured by an infrared detector, and becomes a point in a plot that changes how astronomers understand galaxy formation. Nothing about that needs exaggeration. The real chain is already astonishing. There is a similar chain for exoplanets. Starlight passes through the upper atmosphere of a world hundreds of light years away. A molecule absorbs a few wavelengths. The planet moves out of transit. The star brightens by a tiny amount. Webb measures the difference. Human beings infer chemistry in air they will never breathe. And for star formation, dust hides a protostar. Infrared light escapes. Webb detects it. A young system becomes visible before its planets have finished forming. The telescope repeatedly turns absence into evidence. Darkness becomes dust. Redness becomes distance. A missing atmospheric feature becomes a constraint. A faint spectral bump becomes chemistry. A blurred arc becomes gravitational lensing. This is the quiet intelligence of Webb's science. For the viewer, the episode should feel like a widening lens. It begins with the machine, the launch, the folding, the gold mirror, the sunshield, the cold. Then it widens to Hubble and the reason Webb had to exist. Then it widens again to the first images, where the telescope proves itself. From there, the story opens into the main scientific worlds Webb touches: exoplanets, early galaxies, star-forming clouds, solar system chemistry, dying stars, black holes, and future surveys. The risk in a Webb script is that it becomes a catalog. The solution is to keep returning to one central idea. Webb reveals what was hidden by distance, dust, temperature, or wavelength. Distance hides early galaxies. Dust hides star birth. Temperature hides cool material from optical telescopes. Wavelength hides molecular fingerprints from human eyes. Webb is built to cross those barriers. That gives the viewer a simple thread to follow even when the science changes topic. The telescope keeps doing the same kind of miracle in different places, making invisible information visible. This is why the script can be calm without being boring. Each section has a new object, but the underlying pattern remains familiar. The listener does not get lost in a list. They hear variations on one theme. The mission also has a useful humility built into it. Webb is the most powerful infrared space telescope ever launched, but it is not the final telescope. It cannot do everything. It cannot image an Earth twin around a sun like star in detail. It cannot directly observe the Big Bang. It cannot solve dark matter or dark energy alone. It cannot turn every distant galaxy candidate into a confirmed object without enough observing time. It cannot make stellar activity disappear from red dwarf atmosphere studies. It cannot replace missions that need to land, orbit, or fly through plumes. Its power is specific. That specificity is what makes it trustworthy. A great instrument does not answer every question. It answers certain questions so well that new questions become unavoidable. Webb is already doing that. The early universe appears more active than expected. Red dwarf planets may be harder to interpret than hoped. Star-forming regions are more structured at small scales. Dying stars preserve more complex histories. Dust and molecules appear as central actors rather than background details. This is a mature kind of wonder, not the wonder of having everything explained, but the wonder of finding better mysteries. There is a final practical detail that makes Webb's current science especially valuable. It is observing while the universe of astronomy around it is changing quickly. Roman will bring wide-field infrared surveys. Extremely large ground-based telescopes will study exoplanets, galaxies, and black holes with enormous collecting area. ALMA continues to map cold gas and dust. Gravitational wave observatories are opening another channel of cosmic information. Future missions will be designed partly in response to what Webb has revealed. That means Webb is not only answering old questions. It is setting the agenda for instruments that do not yet exist or have not yet begun full operation. If Webb shows that certain early galaxies are common, future telescopes will be built and scheduled to study them. If Webb shows that rocky planets around red dwarfs often lose atmospheres, future life search strategies will adapt. If Webb finds that disk chemistry differs strongly by stellar type, planet formation models will change. If it finds black holes growing early, theorists will refine formation pathways. A telescope can influence the future not only through what it discovers, but through what it teaches the next generation to look for. That is exactly what Webb is doing now. All of this makes Webb a rare subject. The machine, the images, and the ideas are equally strong. Some space stories have beautiful engineering but abstract science. Some have profound science but little emotional shape. Webb has both. The launch was dramatic. The deployment was suspenseful. The mirror is visually unforgettable. The first images were instantly understandable. The discoveries reach from planets to the early universe. And the central metaphor is simple enough for anyone to feel. A cold telescope in deep space catching ancient light. That is the reason the episode can end quietly. It does not need to force emotion. The emotion is already there in the scale of the thing. That is enough for a strong story. And because the real science is already vast, the script does not need to pretend certainty where the data are still developing. It can stay calm, accurate, and still feel enormous. For this episode, that feeling is the spine. Hidden light becomes visible, and visible light becomes a better question. A listener can follow Webb through one simple feeling. The universe was always richer than our eyes could see, and this telescope was built to let more of it arrive. Not all at once, not as final answers, as measurements, as spectra, as faint red galaxies, as hidden stars, as molecules in distant air, as dust around dying suns, as questions made sharper by better light. The James Webb Space Telescope is, in a literal sense, a time machine. When it observes a galaxy 13 billion light-years away, it is seeing that galaxy as it was 13 billion years ago, because the light we receive left that galaxy 13 billion years ago and has been traveling to us ever since. Looking at distant objects is always looking into the past, but Webb looks further into the past than any optical or infrared telescope before it. It can see the universe when it was only a few 100 million years old. It can see the first generation of galaxies assembling from the first generation of stars. It is watching the universe build itself. This capability, to observe directly what the universe looked like near the beginning, is something that every astronomer who has worked in the field since the expansion of the universe was discovered has wanted. Hubble could get partway there. Ground-based telescopes with adaptive optics could contribute. But the combination of aperture, wavelength range, and stability that Webb provides was specifically designed to go all the way. to see back to within a few 100 million years of the Big Bang, to the epoch when the first structures lit up the previously dark universe. The images Webb has already returned: galaxy clusters bending space, ancient light traveling for billions of years, stars being born in clouds of gas, the carbon dioxide of a planet's atmosphere leaving its fingerprint in starlight, are the product of a telescope that took 25 years to build, $10 billion to fund, and the dedicated effort of tens of thousands of scientists, engineers, and technicians over the course of a generation. The alignment of Webb's mirrors was confirmed complete on March 16, 2022. The image the engineering team used to confirm the alignment, a star in the constellation Ursa Major, designated 2MASSJ 17,554,042 plus 6,551,277, a faint, yellowish object surrounded by thousands of background galaxies, was the first image the telescope produced at its full capability. It showed the alignment had worked. It showed that the telescope was doing what it was designed to do. Someone on the engineering team said, looking at that image, that it looked like the Hubble Deep Fields. A colleague replied, "That is the Hubble Deep Field level. We did it." That is not a bad summary of what Webb represents. A telescope that extends to the infrared, with a mirror nearly 3 times Hubble's diameter, at a stable orbital location where it can be perpetually cold, measuring the universe at wavelengths that reveal its earliest chapters, a telescope that was designed specifically to answer the question of what the universe looked like at the beginning, and that is now answering it. The beginning was not quiet or dark. It was brilliant with the light of young, massive, short-lived stars, surrounded by clouds of gas still raw from the primordial plasma, assembling into the galaxies that would eventually host billions of years of stellar evolution and the chemistry of life. Webb is showing us that beginning, one image at a time, from a point 1.5 million kilometers from Earth, looking outward and backward through time. That is a remarkable thing for a species on a small planet to have built. And it is still operating, still looking, still collecting light that left distant galaxies before the Earth existed. The telescope is still at L2, still cold, still held in shadow by its sunshield, still pointing at whatever the science team has scheduled for tonight. Somewhere in its detectors, photons that began traveling billions of years ago are being converted into data. Somewhere on Earth, those data will become spectra, measurements, papers, arguments, revised models, and new questions. Webb does not show us the literal first moment of time, but it brings the young universe closer than it has ever been, and it does so quietly, one target, one exposure, one photon at a time. The early universe is still out there in the light that has not yet finished reaching us. Good night.